Hey, honors algebra 2, chapter 3, section 4, a little bit of 3 and 4. Goal is to solve system of 3 equations. So we're going to have 3 equations, which means we have 3 variables. So we're going to start off with a system right here, just a general form. So we have x, y, and z in all 3 of these equations. And so you have 3 equations, 3 variables. So when you're ever trying to solve this, your goal is to take and get down to 2 equations, 2 variables. So when you're doing that, you take 2 of the equations, and it doesn't matter which 2, and you eliminate 1 variable. So if you eliminate the z's here, you eliminate the z's, so you get down to just the x and y's in the equation. Then you need to take 2 different equations, and you can choose which 2, but a combination of 2 different ones. So if I just show you the middle and last one, you need to get rid of the z's and those 2 as well. Eliminate those and get down to x and y's. And so now you go from a system of 3 equations, three variables, down to 2 equations and 2 variables. And then you can take these and then now get down to 1 equation with 1 variable. So you can eliminate the, we'll say y's, and only end up with the x's. And then from that you can solve it. And so that's the process in solving it. Now, what a system of 3 equations, if we look at ax plus by plus cz equals e. This equation, if you're plotting it on a graph, it's 3-dimensional. What you actually have is the x-axis and y-axis are actually laid down. So this is like the positive x's, the positive y's. Then we'd have negative y's and negative x's. And then we have our z-axis, which will go up and down. We'd have the positive z's, and we have the negative z's here. And so the positive x's are kind of coming at you. Positive y's are to the right, positive z's are up. And so when you plot this, you really find that the intercepts, similar to what we did in standard form for just the xy 2-variable equation, you could find the intercepts, the x-intercept, the y-intercept, and the z-intercept. And then if you connect them, what you end up getting a lot of times is a plane, a flat surface. And so it's not just the range in here, it's anything on this flat surface here, and it continues on forever in every direction. But so that's kind of the angle. So it's a 3-dimensional graph. And so you don't need to be able to get the graph at all, but you need to understand that when we're solving these systems of equations, we're taking 3 different planes and trying to see how the planes intersect. And so you have some different scenarios on how planes intersect. Not lines, we're talking about planes. And so we're solving the system. One thing we can first do is see if solutions, the points are solutions. So when you're given a point, you're given x, y, z down here. So x, y, z, x is 3, y is 3, and z is 4. And you can plug it into the system. You need to check for all 3 conditions again, similar to yesterday, but we're doing for 3 variables. So when you're testing it, you just need to plug this point into all 3 equations. So for the first one here, I plug in 3 for x, 3 for y, so 2 times 3 would be 6, 4 times z, 4 times 2 would be 8, and then equals 1. And so we have 9 minus 8, which checks. That's 1 equals 1. So I need to try it for the second equation. So same thing, 7 times 3, 21, minus 4 times 3, 12, plus 4 equals 11. That doesn't work out, so then you get 9 plus 11, so 13 does not equal 11. So right there I can stop. I don't need to even check the third equation. I don't care about the third equation. Already is not a solution. No, it's not a solution to the system. So that's just checking points to see if they are solutions. Now for the difficult stuff. We're going to solve systems of 3 equations. And so here's 2 examples I'm going to run through. So for here, when I first look at it, there's an x in all 3 equations. There's not a y, and then there's a z. So because there's not a y in the third equation, to save us some time, I'm going to take the first 2 equations and get rid of the y. That way the third equation is already set up with 2 variables. So we'll go right down to 2 variables, 2 equations of 2 variables. And so to do that, to get rid of the y's here, I'm going to keep the first equation as is. And then I'm going to take the second equation, and I'm going to 2. If I do that, I get 2x plus 4y minus 2z equals 16. Now I can add these. So we get 4x plus 2z equals 28. So for this equation, I also have the third equation already written with just x and y. So I'm going to take this equation we just created, and a third equation which already is isolated to the x and z's, so we no longer have any y's. And so you can write this system. So now we have 2 equations and 2 variables. So now this problem is identical to yesterday's. I would subtract these 2 right away because I have the 2z and 2z. So 4 minus negative 3x is actually 7x. The z's are gone. 28, so x is 4. Now our back substitution. So we have our first variable, x equals 4. I can plug it back into one of these equations up here that only has x and y's. If I do that in this equation, I'm getting 16 plus 2z equals 28, and I plug in 4 for x. 2z, if I subtract 16 to both sides, I get 12, and then divide by 2, so I find z is 6. Now I need to back substitute again. I need to plug in my z value and my x value into an equation that has a y. So if I go back to this original equation, I would choose this middle one. So it would be x, which is 4, plus 2y, don't know why, minus my z value equals 8. So this is 2y equals 4 minus 6 is negative 2. So if I add 2 to both sides, I get 10. So y is 5. Now when I write the point, it's going to be alphabetical order, x, y, z. So 4, 5, 6. So this is the solution to the system. Not too bad for that one. Let's do a more complicated one. Now all 3 of these, they all 3 have x, they all 3 have y, they all 3 have z. So I need to isolate, take 2 of the equations and get rid of one of the variables, the same variable. So when I look at this, I can see I can get the x's the same pretty quick by multiplying 3 in the top one, or multiply the first and last one, making 2. I can get the x's the same quickly. I can do the same thing with the z's. And the z's the same coefficient quite quickly. For this one, I would choose probably the z's. To do that, I would take the first equation and the third equation. If I take those 2 equations, and I'm going to get rid of the z's, so I'm going to add the equations because these z's are opposites. So if I add these 2 equations, I get 3x plus 9y equals 36. So that's adding. Then we'll repeat that process with 2 different equations, a combination of 2 different equations to get rid of the same variable. So if I take this first equation and the second equation. The second equation I'm going to keep the same. I'm not going to change that. But the first equation, I want to have a same coefficient or opposite. So I'm going to multiply this top equation by 2. So 2x plus 10y minus 2z. So now we have the opposite coefficients. Don't forget to do it to the 16. So we have 32 when you multiply by 2. Now I can take these 2 and add them up. So 5x plus 7y equals 44. So now I have these 2 equations. Now, to help me out, I see this equation up here in purple we created. They all are multiples of 3. So if I divide everything by 3, I get this equation, which is an equivalent equation. That helps me out. So now I have these 2 equations, which I need to solve. And you can do it a couple ways. I can keep going with linear combination, or I can use substitution because I have x almost by itself here. I would probably keep going linear combination, so I multiply the purple equation by 5 maybe on both sides. So I get 5x plus 15y equals 60. And again, that's multiplying this equation by 5 on both sides. Now we can subtract these equations. So we get negative 8y equals negative 16. So then if I divide by negative 8, I get y is negative 2. So there's our y value. We need to back substitute that to find x. If I just choose this equation up here, so x plus 3 times negative 2 equals 12. So that's a negative 6. If I add 6, I get x is 18. I gotta do it one more time. I gotta plug them both back into an equation that has x, y, and z. So let's choose this top equation because the x and z's have no coefficients, which is kind of nice. So when I plug it in, we have x is 18 plus 5 times y, which is negative 2, minus z, which we're going to solve for that, equals 16. So we have 18 minus 10, so we have 8 minus z equals 16. So negative z is 8, so z is negative 8. So there are the three values. We will write as a point, we would write 18, negative 2, negative 8. And this is the point where all three of these equations intersect. So they are intersecting at a point. So they're a doozy of a problem. They're not easy. They're pretty complicated, but we'll give it a shot tomorrow. Have a good night.